Hello, welcome back to our series on statistical mechanics. In the last episode, we saw the derivation of partition function for a 3D classical ideal gas. There, we derived that the partition function for a 3D ideal gas can be written as Qn is equal to h raised to v raised to n by h raised to 3n, and then we have the function which is corresponding to the de Broglie wavelength, which is 2 pi m kt raised to 3 by 2. Since we are talking about we were talking about n number of particles, we had n also as the as the exponential. And also we told that since based on the Gibbs paradox, we need to introduce a standardization parameter in the denominator, which was n factorial. So this was the expression which we derived last time for the 3D classical ideal gas. Now, as I told in that episode, once we derive the partition function for any system, for the real life system or the kind of hypothetical systems which are very useful for the further progress of the study on the physical parameters of any system, the Qn expression forms the fingerprint. Now the question is that how to proceed further based on this partition function. There, in one of our very previous videos in the beginning of this series on statistical mechanics, I had given you few expressions connecting the entropy with the various physical parameters. Here, let me list out maybe 3 or 4 expressions which connects our normal thermodynamical parameters to the partition function. First and foremost, the most important expression could be of the average energy per microstate or element, whatever it is, right? Average energy per element, which we designated by U, and we know that it is equal to minus dou by dou beta ln Q. So which means what? Which means that if we know the expression for Q, we can calculate the internal energy or the average energy per element. The next important parameter which we had discussed earlier in one of the series, one of the episodes was the Helmholtz free energy, right? Which we normally designated by A, and the expression is minus kT ln Q, right? So we have the average energy and the Helmholtz free energy expressions over there. And now, which is the parameter which we need? CV, the specific heat capacity at constant volume, which is CV. CV can be expressed in terms of A, which the expression which I had given you in one of the previous episodes. But since CV is important, let me remind that expression, or let me write down that expression once again. Minus T into dou squared A by dou T squared, where A is the Helmholtz free energy, T is the temperature, and we are taking the differentiation with respect to temperature. And the entropy S is equal to minus dou A by dou T. That's very famous expression. The connection between entropy and the Helmholtz free energy. And what else? I can write the expression for pressure as dou A by dou V, minus dou A by dou V. The differentiation with respect to the volume of the system into the Helmholtz free energy. So, so these 4 or 5 expressions tells us that the moment we calculate this partition function, we can calculate the rest of the relevant parameters in thermodynamics, right? Okay. So, to further proceed with this episode, I will be mainly discussing about a new system which I had promised in the last episode. Last episode we were discussing about the 3D classical ideal gas. So, today in this episode we will discuss about a 2D harmonic oscillator. Any physics student will know that classical ideal gas or the ideal gas is the first and foremost system which is important for any physics student. And another main thing which we analyze is the harmonic oscillators. So, within the 2D harmonic oscillator, we can have 2 different kinds of approaches. One is the classical and another is the quantum mechanical. To start with, so that we really continue with the classical approach we had in the last episode, let me specifically discuss to start with the classical case, which is the 2D classical harmonic oscillator, right? If the time permits, we will have discussion on the quantum mechanical harmonic oscillator also. How to start with? To give you a more flavor, unlike the previous time, episode for the ideal gas situation, let me take up a new approach over here, which is also an accepted format for the statistical system. So, this will give you a new way of doing the problem, which will give you more flexibility for any kind of system which you would like to analyze. So, here we will try to start with a single particle partition function, which I had discussed last time. If you remember, last time towards the end of the episode, we did connected the n particle partition function with a new idea called the single particle partition function. So, here in this episode, let's start with the single particle partition function. So, if I write down the single particle partition function in the case of a classical situation, which we discussed last time, that it's a continuum. So, therefore, we can use an integral instead of the summation. If you remember, so Q1 is equal to integral 0 to infinity exponential minus beta e, and then we need to have the weight factor, right, which is accounting for the degeneracy of the system, which we put as GE D, right. So, this is the first expression or the first opening equation with which we can derive the partition function for the 2D classical harmonic oscillator. And when the moment we hear about a classical harmonic oscillator, we are asked to write the energy for the classical harmonic oscillator. How to write it? There are various ways of writing it, but the the most prevalent way of writing it is writing it is in terms of the momentum, right? So E is equal to P squared by 2m plus, this is the kinetic energy part, and then we have the potential energy part, which is half m omega squared q squared. If you remember, we are still continuing with the phase space analysis or the phase space treatment for our space for any example which we take up. So therefore we have the P and the Q as the coordinate for the system, right? So we have the energy over here. Now our task will be to calculate this GED, right? Now how to do it? If you remember last time, what we did was that we were imagining a 3D space, and we were imagining that our ideal gas was enclosed within a spherical space. There we took a shell and we took the volume of that shell, and we calculated the number of particles or the number of microstates which are there in that shell. Here we are talking about a 2D situation, right? So therefore naturally we don't assume a sphere, instead we will assume a circle. If you remember from your 12th class thing, a 2D symmetric harmonic oscillator will have its oscillation centered like a circle, right? Where we have the x-axis and the y-axis which are perpendicular, and correspondingly we have the frequencies omega x and omega y as the corresponding frequencies. This is a very, harmonic oscillator itself is a very huge section where we can have a lot of Lissajous figures being derived based on the movement of the harmonic oscillators. But in our derivation, we will be simply sticking on to the basic situation, which is a symmetric harmonic oscillator, which is making its vibration or making its oscillation in a symmetric manner. So this is the situation which we will be dealing with, right? Yeah. So now the question is that how to find out this number of microstates. So how to deal with that? As I reminded you, similar to the case of your classical 3D gas, classical ideal gas, here also we will be calculating the area. Area of what? Area of the phase space in two different coordinates. One is the Q and the another is the P. So we have a Q space. So we need to calculate the area of the phase space in that space and area of the phase space in the P space. Now let me try to write it down for you. Number of microstates is equal to area of the 2D space between P and P minus dP, right, into area of phase space between Q and Q minus dQ. While, yeah, so I will come back to that, but and then divided by what? So these are the areas. So if we need the number of microstates, we need to divide it by the area of the single microstate, right? So what is the area of single microstate? In the previous episode we had derived that, and that was H, right? And here we have a P space and a Q space, and therefore H into H squared. So we in the denominator we have the H squared. So yeah, so what I was trying to tell earlier was that between P and P minus dP, which means that what? Which means essentially my figure is like this, right? I have a two-dimensional circle or two-dimensional space where I assume that this is P and this is P minus dP, because this dimension is the thickness of the shell is dP. But in some textbooks or in some books, you can definitely take another way of doing the same thing, where you take the P as this one, the inner shell, the inner area, and take the outer area as P plus dP. But mathematically it does not make any difference. Our effort is only to calculate the area of this shell, right? So if you take P plus dP or P minus dP, your mathematics will be of that kind, and then you can evaluate them like that, right? So how did we did last time? You take the area corresponding to P plus to P minus P minus dP, and then we will neglect the dP squared terms. We will neglect the dP squared terms because the dP is a very small space, and therefore dP squared can be neglected safely, right? And therefore, in that situation, you can evaluate for yourself, and then you will find that that factor, we can write the expression over here as 2 pi P dP into 2 pi Q dQ divided by H squared. So this is the number of microstates, which is what? Which is actually my GED, or my degeneracy. So I have just calculated the GED. Now if I go back to the expression over here, which we wanted to start with. So now we have calculated the energy over here, and we have this factor also being calculated. Now our task should be to just simply supply those things over to here, right? So let's do that now. Right, if I substitute those parameters of energy and the GED, I can write the expression as Q1 is equal to double integral 0 to infinity, double integral because I have two parameters, right? Which is 2 pi P dP divided by H into 2 pi Q dQ divided by H into my energy expression e raised to minus beta E, which is E is equal to P squared by 2m plus half m omega squared Q squared. So therefore E into minus beta P squared by 2m plus half m omega squared Q squared, right? So this is the expression which we need to integrate. For our convenience, since we have the double integral, let's split this double integral into two functions, right? One will be the function of the P in terms of the P dP, and another will be in terms of Q dQ. So if I split it, I can write this as equal to 4 pi squared by a squared, the common factor I took it out of this expression, and then I can write it as integral 0 to infinity what? E raised to, let the first term be in terms of the p, e raised to minus beta p squared by 2m into PdP, this PdP into, I have taken the common factor outside, therefore I need not worry about that, e raised to minus beta into half m omega squared q squared q dq. Right. So, this is the expression for my single particle partition function. Now, our task is to do the integration. Excuse me, I forgot to write this expression, that integral over there. Right. So, we have the two factors. So, first we can do this integral, we can do this integral, and then simplify, then our task will be easier. So, how to do that? In order to do that, let us assume that p squared is equal to x. X is equal to p squared, which means what? Which means that if I do the integral, dx is equal to 2p dp. 2p dp, right? So, I will substitute that over there, right? So, in wherever I have p in terms of p, I can substitute that over there and carry out the integration. So, you can do that. Now, if I let me invoke a standard integral which will make my life easier, right? Which I will write it as integral 0 to infinity x raised to n e raised to minus alpha x dx is equal to, this is the normal factor for the gamma function, which is n factorial alpha raised to minus n minus 1. So, this is the standard expression for doing this kind of derivation. So, this is actually that expression can be supplied over here to simplify that expression over there, right? So, if I substitute that, I can write this as equal to LHS is equal to half integral 0 to infinity e raised to minus alpha x dx, which is e raised to minus beta x by 2m dx, right? If I substitute this kind of the identity, I can write it as equal to half 0 factorial beta by 2m raised to minus 1 So, one of the integrals which we had in this integral, especially this integral, after substituting for x is equal to p squared and utilizing the identity we had over here, now we have reached to a stage where I can put that integral which was there in that square bracket can be equal to this one. What is beta by 2m? Beta is equal to 1 by kt, and therefore I can write this expression as equal to beta is equal to 1 by kt, right? And therefore I can, and I have the raised to minus 1, which means that is my reciprocal. Therefore, I can write this as equal to mkt. Right. So, this is the factor for the first integral which we saw, and therefore, our task is now to evaluate it for the second integral. So, if we calculate the second integral means what? This factor over here, right? Now this we have already calculated that this is equal to mkt. Now the task is to find out the second factor. In order to calculate the second factor, we can use the same expression or the same identity which we utilized over here and make it simplified. Only thing is that it will be in terms of the q dq, which means what? Which means that I can write it as e raised to integral 0 to infinity e raised to minus beta half m omega squared q squared into q dq. If I substitute this integral, I can write this as the second one, second square bracket factor as equal to half 0 factorial. That was m omega squared k squared. Therefore, I can write m omega squared by kt. Right, m omega squared by kt raised to minus 1. So, so we have this expression, and then we can simplify that as equal to kt by m omega squared, right. So, this is the expression for our quantity in the second bracket. Now what? Now we go back to this expression. So, now we have 4 pi squared by h squared into mkt into m omega squared by kt, which we put together, right. We can put together and write it as equal to 4 pi squared by h squared into mkt into into kt by m omega squared, which is equal to 1 by h squared omega squared beta squared. So, this is the expression for the for q1. Now, the question is that what will be the partition function for the entire system of n number of particles, and that I can write in terms of n as qn is equal to q1 raised to n. Since we are not dealing with a classical ideal gas, we need not account for the paradoxical situation or the indistinguishability of the particle need not be taken into consideration over here, and therefore I can just simply scale it by n and write it as 1 by h squared omega squared beta squared raised to n. So, this is the partition function for a classical 2D harmonic oscillator. So, in this episode, we essentially saw how does how can we connect the partition function to various thermodynamical parameters, namely average energy, entropy, Helmholtz free energy, heat capacity at constant volume, etc. And then we took a specific case of a 2D harmonic oscillator in a classical situation, and we tried to analyze or derive its partition function. And then we reached this expression, and similar to the case of 3D classical ideal gas, we can also calculate, or you can try yourself to calculate the other thermodynamic parameters which are correspondingly. Now, I would like to do the evaluation of the partition function for a 2D harmonic oscillator in a quantum mechanical regime, which we will do in the next episode. Thank you.